All right, we're here with some vocabulary and the first example from 8-7, which is on special right triangles. The words that we're accountable for here are 45-45-90 triangle, a 30-60-90 triangle, and apothem. So I have the definitions already right here. All right, folks, we're going to go over a couple of vocabulary words. And first example from 8-7 in geometry, which is on special right triangle. So the words here that we need to be familiar with here are a 45-45-90 triangle, a 30-60-90 triangle, and an apothem. So we'll talk about what each of these things are. A 45-45-90 triangle is an isosceles right triangle whose angles are 45, 45, and 90, hence the name 45, 45, 90. These are referring to the angle measures of a right triangle, and it's a right triangle because it has a 90-degree angle. And then it's an isosceles triangle because it has two angles that are the same measure. So that's what a 45, 45, 90 triangle is. We'll see a picture of that in just a moment. A 30, 60, 90 triangle is very closely related. It's a right triangle in which the three angle measures are 30, 60, and 90. So it's a right triangle because it's 90 degrees, and then the other two angle measures are 30 and 60. This is a special type of right triangle that has some properties that we will take a look at here momentarily. And then an apothem is the perpendicular segment from the center to any side of a regular n-gon. That's not confusing at all. It's the perpendicular segment from the center to any side of a regular n-gon. That might not do much for you, but when we see a picture of it and what it looks like here in a couple of minutes, that will make a lot more sense as to what exactly that is. But first, let's talk about a 45, 45, 90 triangle. That's what I have here. This is a 45, 45, 90 triangle because it has two 45-degree angles, as indicated, and then a right angle of 90 degrees. So this right here is a 45, 45, 90 triangle. And as a result of that, it's also a right triangle. So the Pythagorean theorem will hold true, which we'll test in just a minute here. And then this side length right here is the same as this side length. They're both x because this is also an isosceles triangle. This angle is equal to this angle here. Therefore, those sides that are opposite those angles have to be the same. And that's from what we know about an isosceles triangle. This side length here is labeled C because this is the hypotenuse of the right triangle. So what we can do here is use the Pythagorean theorem to kind of look at the relationships of these sides. So what I'm going to do here is just plug these values into the Pythagorean theorem. We have C squared, the hypotenuse squared, is equal to the two legs, the sum of the two legs squared. So A squared plus B squared is equal to C squared. I kind of have that written backwards there, but take this side length squared plus this side length squared. They're the same because it's an isosceles triangle, is equal to this hypotenuse squared. And then we can combine some like terms here because x squared plus x squared is 2x squared. So 2x squared equals c squared. And then what we can do is take the square root of each side. The square root of c squared is c, and the square root of 2x squared is x, because the square root of x squared is x, times, because we're multiplying these two things here, square root of 2. So c is equal to x times the square root of 2. And what this does here is it shows the relationship of the sides of a 45, 45, 90 triangle, which brings us to the isosceles right triangle theorem that says that in an isosceles right triangle, this thing right here, if a leg has a length of x, so whatever that leg length is, then the hypotenuse has a length of x times the square root of 2. So what does that look like in practice here? It looks like this. We have a 45, 45, 90 triangle, and we want to find the missing side lengths. Looks like I already have one there, so that shouldn't have been there, but it's there anyway. These two are going to be the same because this is an isosceles triangle. This is 45 degrees. This is 45 degrees. So therefore, these two sides here have to be the same because of the fact that this is an isosceles triangle. But we can still find this side length right here. So Going back to the isosceles right triangle theorem, says that in an isosceles right triangle, if a leg has a length of x, in this case that x is 6.4, then the hypotenuse has a length of x times the square root of 2. Well, here's our x, right here, 6.4. Therefore, this side length is going to be 6.4 times the square root of 2. No Pythagorean theorem necessary, because since this is a 45, 45, 90 triangle, we know the relationship of the leg to the hypotenuse, which is the length of the leg, times the square root of 2, will be the length of the hypotenuse. Another example here, also a 45, 45, 90 triangle, because this is 45 degrees, this is 90 degrees, so this angle also has to be 45 degrees because the three angles in a triangle add up to 180 degrees. So this is a 45, 45, 90 triangle. So the isosceles right triangle theorem works here. However, this time we have the hypotenuse. We have 10, and we're looking for the two legs. Now we know that these two legs are the same because it's an isosceles triangle. This 10 here is going to be equal to x times the square root of 2 from that isosceles right triangle theorem. That's what this is. This is x times the square root of 2. 10 is the same as that because it's the hypotenuse in this case. So now we're going to solve for x. So to solve for x, we're just going to divide both sides by the square root of 2 to get x by itself. X times the square root of 2. So if we divide by the square root of 2 on both sides, we'll get x by itself. This looks like this might be a nice answer, but it's not, because we don't want to have radicals or square roots in the denominator when that square root is not an integer, or when that square root, we're not taking the square root of a perfect square. 2 is not a perfect square, so this is not okay to leave. So we need to eliminate the square root of 2, or just the square root in the denominator. And how we're going to do that is create an equivalent fraction by multiplying the numerator and the denominator of that fraction by the square root of 2. Because if I have a fraction and I multiply the numerator and the denominator by the same number, the fraction maintains its equivalence. It doesn't change the value of the fraction. So I'm going to multiply the numerator and the denominator by the square root of 2, because when I do the square root of 2 times the square root of 2, we get 2. And then I can take 10 times the square root of 2, and that simplifies to 10 times the square root of 2 over 2. That's this multiplication simplified. This fraction is exactly the same as this fraction. It's just that there's no radical or square root in the denominator. And this can actually be simplified further, because 10 square roots of 2 divided by 2 is just going to be 5 square roots of 2. Therefore, these two lengths are going to be 5 times the square root of 2 and 5 times the square root of 2. They have to be the same because it's an isosceles triangle.